Hey, how's it going? We're going to be looking at some practice stoichiometry problems. These are the four examples that you will find on your Introduction to Stoichiometry notes. Now I want to draw your attention to this image again and show you the different types of problems you might see. First of all, keep in mind that whenever we do any stoichiometry problems, we're going to compare two different substances. In this case, we'll call them substance A, substance B. So of course you'll have a balanced equation and two different substances from that equation will be mentioned. So you want to focus on whichever two substances those are. If you're starting in moles, then all you need to do is switch from A to B using the mole ratio that exists between these two substances given to you by the balanced equation. If your goal is to end at moles, then once you've switched over, you're done. However, sometimes you may not start in mole, and you may not want to end in mole, so there are conversions that may happen either from mass to mole, volume to mole, or particles to mole. Typically, the most common example, and the four examples you see today, will include mass only. So can you convert a mass to a mole? Yeah, of course, you use the molar mass. Now that you're in mole, use the mole ratio again to switch from A to B. Oftentimes you'll stop at moles, or you'll convert that to mass of substance B using the molar mass of substance B this time. We may ask you to stop at volume or stop at particles. Any of these could happen, but again, mole to mole, mole to mass, mass to mole, or mass to mass are the most common examples, all which require a mole to mole ratio as your conversion factor to allow you to switch from substance A to substance B. How many moles of KClO3 in example 1 must decompose in order to produce 9 moles of oxygen gas? So here's your balanced equation. You can see we have a 2 to 2 to 3 ratio. Now in this case, we really only care about two substances. That's KClO3, which is here, and oxygen, which is here. So we know we're going to use this 2 to 3 ratio as our conversion factor to switch from substance A, oxygen in this case, to substance B, KClO3. We're starting with 9 moles of oxygen gas. That's the only number, the only quantity given to us in the problem. And we want to take this and see how many moles of KClO3 must decompose. Well, you're going to see this one, you actually don't need to use any math. We can clearly see from our recipe or our balanced equation that if we have 2 moles of KClO3, that could decompose and form 2 moles of KCl and 3 moles of O2. Well, we know if we don't want 3, we want 9 moles of O2. We can see that this is only going to triple to get to 9, so then this of course will have to triple to 6. So if we want to make 9 moles of O2, we'll need to start with 6 moles of KClO3, and you can clearly see that because it is a direct mole ratio with very easy numbers that can be divided easily. But let's go on with the math anyway. We don't want moles of O2, so to cancel this, we put the matching unit on the bottom. Moles of O2 will go down here. And we want to switch to moles of KClO3. Well, the only way to relate those two is using the mole ratio. 2 moles of KClO3 for every 3 moles of O2. This is the new relationship again, the mole ratio, that allows us to switch from substance A over to substance B. And we use the coefficients that we had in our balanced equation. This can happen once you're in moles, and it will leave you in moles. From substance A in moles to substance B in moles. And in this case we're good stopping at moles. Of course, moles of O2 cancels. 9 times 2 divided by 3. Of course you get your answer 6, which we already knew it would be, but We went ahead and did it anyway. Pretty simple, and this is it. This is really the only new step right here. Your mole ratio, which comes from the balanced equation, which converts you from A to B. Now the rest are going to be the same way, except you're going to have an additional conversion either from mass to mole or in the end from mole to mass. So you're going to start seeing grams getting involved. Again, two substances, H2O and O2. Well, looking at the equation, we see 2 moles of H2O will produce O2, assuming a 1 here when there's no number written. So we're going to need this mole ratio of 2 to 1 at some point. Now the only quantity we're starting with is 5 moles of O2. We don't want moles of O2, so we want to reduce this by putting it down here. Now that we're in moles of substance A, we can convert it to moles of substance B. In this case, B would be H2O, the other one we're comparing it to. Well, moles of O2 goes on bottom, moles of H2O goes on top, and we see it's a 2 to 1 ratio. 2 moles of H2O to every 1 mole of O2. Now that gets rid of moles of O2. If we wanted moles of H2O as an answer, we'd be done. But they wanted us to go a step further and address, well, how many grams is that equivalent to? In order to convert from moles to mass in grams, of course we know to use the molar mass. So get rid of mole of H2O by putting it down here. And to go to grams, you find the molar mass in the periodic table and put it on top. 2 hydrogens plus 1 oxygen gives us a mass of 18.02 grams of H2O for every mole of H2O you have. Moles of H2O cancel, and the mass, which is the unit we wanted, is now the unit we have. 5 times 2 times 18.02 divided by 1 divided by 1. 2 sig figs to start with. So our answer expressed to 2 sig figs is 180 grams of H2O. So again, notice the only new step that we've seen is applying this mole ratio here, which we got by using the coefficients from the balanced equation. And then we just tied in something we've already done before, which is converting from moles to grams. The other variation you'll see is starting in grams, converting it to moles before hitting the mole ratio, stopping at moles, or possibly going on to grams. Example 3. Here's your balanced equation, and we have NH3 referenced in the problem, as well as NO. So we're going to see we're going to involve this 4 to 4 ratio somewhere in this problem. Now our starting quantity is 824 grams of NH3. Notice now we're starting in grams. We can't switch from substance A, which is this NH3, to substance B, this NO, without using the mole ratio, which requires us to be in moles. So we have to take this mass and convert it to moles. The only way to do that is to use the molar mass. We don't want grams of NH3 down here. We don't want grams of NH3, so to get rid of it, we'll put it down here. And we could use the molar mass to get us 2 moles, knowing that 1 N and 3 H's altogether have a mass of 17.04 grams per every mole of NH3. We could cancel our unit of grams, and now we're in moles of substance A. Now that we're in moles, now we could go ahead and use this 4 to 4 mole ratio. 4 moles of NH3 here for every 4 moles of NO, switching us from A, getting rid of its units, to substance B. And because we only wanted to know how many moles of NO, then we're done with moles as our unit. 824 times 1 times 4 divided by 17.04 divided by 4, and you get an answer of 48.4 moles of NO. So hopefully by now you're kind of getting the hang of it, and you're kind of seeing again the only new step would be this one here, using the mole ratio from the given equation. The rest is stuff we've already done, converting from mass to moles. So this last example will take you all the way across. Again, here we're sticking primarily to mass. We have 12 grams of copper. How many grams of silver? Now be careful, this is copper, but it's not copper. It's the element copper, part of the compound copper nitrate. This is silver's symbol, but it's not silver. This is the compound silver nitrate. So whenever we talk about copper, we mean just copper. Whenever we talk about silver, we mean just silver. So not these, but certainly the two box ones. So 12 grams of copper needs to be converted to moles using its molar mass in the periodic table. There's a 1 mole of copper for every 2 mole of silver ratio, which gets rid of moles of copper and switches us to substance B. We had to get to moles to use the mole ratio. Now we don't want moles, we want to convert back to grams, but now grams of substance B. So 1 mole of silver is 107.87 grams according to the molar mass in the periodic table. So you can see the setup. Again, you can see also this only being our new step, this mole ratio. The rest using molar mass for conversions. Multiply the top, 3 sig figs. 12 times 1 times 2 times 107.87 divided by 63.55 divided by 1 divided by 1. And rounded to 3 sig figs, you get an answer of 40.7 grams of silver. Alright, I hope this helps and gives you a better idea of how to approach these stoichiometric problems. Again, focus in on what you already know and just look for that mole ratio. Make sure you're in moles. Alright, thanks for watching.